Chapter 10 is on alkenes. So if we remember, alkenes are the functional group where I have at least one carbon-carbon double bond. So chapter 10, alkenes. So remember these guys. I'm going to have at least one double bond between carbons, right? So I have at least one pi bond. Remember, a double bond is made up of one sigma bond and one pi bond. Those carbons then are bonded to two other things, whether those are hydrogens or other carbon-based groups or a halogen, it doesn't really matter. As long as I have a pi bond between two carbons, it's going to be an alkene. So those carbons are sp2 hybridized, right? They have one sigma and that looks like a delta, not a sigma. One sigma and one pi bond, right? That double bond is a pi bond. And because of that, we remember our pi bonds, they overlap above and below the plane. So carbon sp2, so I have 3 sp2 orbitals, another carbon with its 3 sp2 orbitals, and then the p orbitals, right, were perpendicular, right? Those guys are unhybridized, and they overlap above and below that pi bond. Right, it's perpendicular to the plane of the 3 sp2 orbitals. Because of that, right, it lacks free rotation. Remember, a sigma bond, right, if I have something that's sp3 hybridized, they only overlap in one spot, and I have rotation around that bond. Because of that pi bond, I don't have free rotation. So there's restricted rotation. So if I was to have, and we talked about this already when we were talking about cistrans, right? If I was to take 2 carbons and let's just bond 2 carbon-based groups to them, if they're on the same side, that's actually different than if I bond them on different sides, right? If I did this with something that was sp3 hybridized, right, just a regular sigma bond, if I do that, and then I do have some hydrogens, kind of messy, sorry, but because I can rotate it, right, it's the same thing as if I was to draw them on the same side because I have free rotation. I don't have that when I have pi bonds, so that makes these guys actually different, right? These would be stereoisomers. Remember, stereoisomers are isomers that differ only by their orientation in 3-dimensional space. So I have the cis one on the left and the trans one on the right, so cis-trans stereoisomers. We are going to add to that. I talked about that in the last chapter. Remember, cis-trans only apply when I have something that's di-substituted. As soon as I add a third group on there, we can't use cis-trans nomenclature anymore. We have to use a different way to name it, and we will talk about that in this chapter. Right now, I just really want to talk about the fact that they're sp2 hybridized, right? I do have a pi bond, and because of that, rotation about that bond is restricted. The other thing I want to talk about before we get into actual nomenclature is calculating our degree or index of unsaturation. Right? Our alkenes are unsaturated. And then we just want to remember that one double bond or one ring is 1 degree of unsaturation. And then in chapter 11, we're actually going to have triple bonds, and a triple bond actually counts as 2 degrees of unsaturation. So what we do is we have a little formula for calculating the degree of unsaturation. And then based on the degree, we have some combination of double bonds or rings or triple bonds. So our formula, it was the number of hydrogens it should have if saturated and then from that we're going to subtract the number of, and I'm going to put it in quotes, hydrogens it does have, I'll explain, I promise. And then we're going to divide that by 2. So the first part, the number of hydrogens it should have if saturated, that's where we use the CnH2n plus 2 formula. So if I have 5 carbons, I should have 2 times 5, which is 10 plus 2, so 12 hydrogen to be saturated. So if I have 5 carbons, it should have 12 hydrogens if saturated. So that would be the first number. For the number of hydrogens that it does have, we're going to count every hydrogen, but then if there's a halogen, we're actually going to add a hydrogen. If there's a nitrogen, we're actually going to subtract a hydrogen, and then oxygens we ignore. So if an oxygen, we ignore it. If a halogen, we're going to add 1 hydrogen for every halogen. Sorry guys, I'm losing my voice. And then for nitrogens, we're going to subtract 1 nitrogen for every, 1 hydrogen for every nitrogen. So some examples. C2H4. So the number of hydrogen that it should have, I have 2 carbons, so 2 times 2 is 4, plus 2 is 6. So I should have 6. I don't have any nitrogens or oxygens or halogens in this one, so just how many hydrogen do I have? 4. And then I'm going to divide that by 2. So 6 times 4 is 2, divided by 2 is 1 degree of unsaturation, meaning that this molecule would have 1 double bond. With 1 degree, remember a ring, if I go back up, a ring is an option, but I can't make a ring out of 2 carbons. That's just not possible, so this one's going to have a double bond. It's my real only option for this. If we do C3H6O, so this time I have 3 carbons, so 3 times 2 is 6, plus 2 is 8, so it should have 8 if it's saturated. I have 6, there's an oxygen there, we just ignore it completely. So 8 minus 6 is 2, divided by 2 is 1 degree again. So this one, I could have 1 double bond, or I could have 1 ring. I can't have a triple bond because I have to have 2 degrees to have a triple bond. Which we do C8H9N. So I have 8 carbons, 8 times 2 is 16, plus 2 is 18. I have 9 hydrogens, but I also have a nitrogen. So I have to subtract a hydrogen for every nitrogen. So 9 minus 1 is 8. So I'm going to subtract 8 from this, and then divide by 2. So 18 minus 8 is 10. 10 divided by 2, I have 5 degrees. So for this one, any of these combinations add up to 5. So I could have a ring and, I don't know, 4 double bonds. I could have 2 triple bonds and 1 double bond. Any combination that adds up to 5. C6, H11, Cl. So 6 carbons, 6 times 2 is 12, plus 2 is 14. I have 11 hydrogens, plus I have a halogen. If I go back up, we need to add a hydrogen for every halogen. So 11 plus 1 is 12, divided by 2, and I have 1 degree again. So a ring or a double bond, no triple bonds in this one. Due to the formula, be able to calculate the number of hydrogens that it should have using this formula for saturation. From that, subtract the number of hydrogens, again in quotes, that it does have, because if it has a halogen, we're going to actually add 1. If it has a nitrogen, we're going to subtract 1. Oxygens, we can just ignore completely. So subtract those two, right, what it should have, what it does have, and then divide it by 2 to get our degree of unsaturation. So I'm going to start nomenclature next. I actually want to name alkenes and alkynes together. So the alkyne part is coming from chapter 11, but the naming is very similar, so I'm just going to group them together. So we are going to use IUPAC again. So nomenclature, IUPAC. And again, I am going to do alkenes, which is this chapter. We just said that those have a double bond between them. And then I'm going to do alkynes, which is going to be chapter 11. And those have a triple bond. So those ones are sp hybridized. There's only one other thing attached to both of those carbons. So this one is chapter 11. Though we are in chapter 10, I'm just going to do both of them now because it's, like I said, it's very, very similar. So our ending for our alkenes is going to be -ene. Our ending for alkynes is going to be -ine. So anes was ane, right? Alkanes, methane, ethane, propane. Alkane ended in ane, so ane is its ending. Alkene ends in -ene, so ene is its ending. Alkynes end in -ine, so -ine is its ending. So if I had a 3-carbon alkene, because there's 3 carbons, and then ene because there's a double bond, so propene, we do need to say where that double bond is. If I have 3, there's only one option. It's I'll write this in a minute, but we're always going to start numbering at the end closest to that double bond. So it's always going to be 1 propene, no matter which way you do it from. So you don't actually need the 1 for that one, otherwise you normally do. So anyway, our ending, sorry, I'll try to be a little more organized here. Our ending for alkenes is -ene, alkynes is -ine. When we number our parent, you want to start at the end closest to that double bond or triple bond. So number the parent starting closest to the double or triple bond. We're going to learn to name each of them separately, so just alkenes and just alkynes, and then eventually we'll actually mix them together. So we could have an alkene and an alkyne, and maybe even an alcohol and an ether on it. So we'll start mixing functional groups. Right now I want to do just alkenes or alkynes separately. So number the parent starting closest to the double bond or triple bond. If there's more than one, you want the lowest numbers for them. So just like we've been doing, I want the sum of the numbers where the double or triple bond starts to be the lowest sum possible. If symmetrical, so if the same numbers from either end, then you want the lowest number for substituents. If that's still symmetrical, then alphabetically. These are the same rules essentially that we were doing for alcohols. So we wanted to number the parent starting closest to the carbon that contains the hydroxyl group, right? If more than one, lowest sum. If the same from either end, then you're going to number for the substituents, right? Lowest numbers. If still symmetrical, then number alphabetically. This is going to kind of be the rules for all of our functional groups. Whatever the highest priority group is, you always want to start numbering closest to it. It's going to trump substituents. Remember, as ethers and epoxides were just substituents, so I didn't have to worry about that. But alcohols actually have their own ending, as do alkenes and alkynes. So they're going to trump substituents as far as numbering a parent goes. So kind of an example. If I was to do this, right, my parent, oh, and I didn't write this, I forgot that with alcohols too, I think. my parent has to contain all of the double or triple bonds. I'll go back and write that. But if it has more than one, all of them need to be in the parent. Unless it's not possible, we do have a couple common names, which I can show you. But if I start numbering from the left, I have the substituent on carbon 2, but then my double bond doesn't start until carbon 3. If I go the other direction, my double bond starts on carbon 2, so that's what I want. That double bond is going to trump that substituent, so I want to go in that direction. So let's write our little note. The parent should contain the double and or triple bonds. So it might not necessarily be the longest continuous chain anymore. It's going to be the longest continuous chain containing those double or triple bonds, right? If I went and did this, oops, it's gotten just way too messy. Way too messy even for me. So let's say I have a double bond here and a double bond here. Actually, it's not, sorry guys, I'm making this up as I go, obviously. And say I have this. My parent actually needs to be, highlighter might work better, needs to be this, right? That has 1, 2, 3, 4, 5, 6 carbons in it. If I go straight across, 1, 2, 3, 4, 5, 6, 7, 8, so that's longer, but it doesn't contain the one double bond that's going down. If I went this part, I can probably just undo it, right? If I did this, it's going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons, but it doesn't contain that double bond that's not part of the ring. So my parent has to be that part. It needs to contain all of those double bonds. When I number this one, I'm going to start here because I want the lowest sum. That's a 3, 4, 5, and 6. So putting the name together, it's very similar to how we put the name together with alcohols. So I have to have the number, this time it's going to be where the double bond starts. It's always between 2 carbons. We want where it starts. So like my first example, the one on the left, the double bonds between 2 and 3, I'm going to put 2 for where it starts. So it's going to be a carbon number, substituent, and then there's still the old and the new method. So the older method, the carbon number where the double bond starts, and then the parent. The new method, the first part of the parent, the number where the double bond starts, and then the ending. So let's just do the first one here. On the 4th carbon, I have a methyl group, so 4-methyl. And then the older method, I'm going to do 2, because that's where the double bond starts. There's 5 carbons, so pent, it has a double bond, so ene. 4-methyl, 2-pentene. This one does happen to be trans, so we could put that out in front. That should go here. So trans would go in front. If I was to use the newer method, trans again, methyl, and then pent, and then the 2, and then the ene. So either one of those methods works. It just depends which edition of the text you have as to how your answers are going to be when you look them up. Both methods are still fairly common, so I would be familiar with them. The second one, because I have more than one double bond, we actually use the diene. Remember, if we had 2 alcohols, we would diol. But if I had 2 methyl groups, dimethyl. So it's going to be diene because I have 2 enes, right? 2 alkenes. If I have 3 triene. And actually, when I write them, I actually put an A in front of it. It's kind of weird. If more than one, or triple, it would just be ine instead of ene. Use, that's an A, diene, triene. It'll sound better when we put the name together. We could do diene. triene. So naming the one up there where I've kind of run out of room, I have a 1, 2, 3, 4, 5 carbon group on carbon 3, so 5 pentyl, right? That's my substituent. And then using the old method, on carbon 1, I have a double bond that's starting. On carbon 3, remember we always put commas between numbers, I have 6 carbons, so hex, and then a diene. Ooh, diene, sorry. I'm making that into a triple bond on you. Diene. The other method, 3 pentyl, hexa. Sorry, the A, maybe we should space that out different. I'm so used to the other method. Hexa, 1, 3, diene. So let's do an alkyne example, sorry. These are sometimes a little weird to look at because they're sp hybridized. They are linear, so just be careful for that. So something like this. The parent might be a little weird to look on this one, but it's going to be this, right? I want the longest continuous chain, and then it needs to contain that triple bond. But I also need to be able to name the substituents. Remember that ether group is just a substituent. So I'm going to have in carbon 1, 2, 3, 4. Right, this might be ugly, but I'm going to grab a different color highlighter. If I did this, 1, 2, 3, 4, 5, there's more carbons, but then I don't know how to name this substituent. So if you're wondering why I went that way, because of that extra carbon there, I can't name it like that. The only way I can name it is if I have the 4 carbons with the ethyl group on. So just be careful as to how things are attached, right? If I have some weird carbon, you can't just make up a name. So my parent needs to contain that 4th carbon the way I have it now, and then I have an ethoxy group on that carbon. So the name for this one, I have on the 3rd carbon an ethyl group, on the 4th carbon an ethoxy group, and if I was to alphabetize those, ethoxy actually comes before ethyl, right? The eth part's the same, but then with ethoxy I get to an O, with the ethyl I get to a Y, O becomes before Y in the alphabet. Oop, not ethoxyl, ethoxy. Ethoxy. So 4 ethoxy, 3 ethyl, and then 1 butine using the older method, 4 ethoxy, 3 ethyl, but 1 ine using the newer method. So if I have both, I'm going to do an alcohol, which is the alkene first, and then we'll add the alkyne, and then we'll add all of them. So if both an alcohol and my double bond, the alcohol actually takes priority. Let's do this. So if both an alcohol and a double bond or a triple bond, the alcohol is going to take priority over both of those. So if I have an alcohol and an alkene, the alcohol takes priority. If I have an alcohol and an alkyne, the alcohol takes priority. Essentially for us in this semester, in 236, you're going to add a lot of other functional groups. But in 235, the alcohol is going to be the highest priority group we have. Because it takes priority, because it's our highest priority group, we want to number the parent starting closest to it. So it gets the lowest number when numbering the parent. So the carbon with the hydroxyl group So the carbon with the hydroxyl group gets the lowest number, right? Number the parent, starting closest to the alcohol, right? It takes priority. So everything is based on it. And then when I name it, it gets to be the end, the very end, because it gets the, priority. It gets the final say. It's kind of how I think about it. So an example, I'm going to put an alkene there on carbon 2, and then going from the other direction, I have my alcohol also on carbon 2. So my parent, just straightforward, is this, but because my alcohol takes priority, when I number it, I want to start numbering on this end, right? I want the hydroxyl group to get the lower number. If I started on the other end, then my hydroxyl is on carbon 4, my double bond starts on carbon 2, but again, the alcohol takes priority. So it gets the lowest number. And then also when I put the name together, it gets to be the ending. And this is where the new method for naming really seems to work better. So I have 5 carbons. I don't have any substituents. So 5 is pent. And then I'm going to put on the 3rd carbon, I have an ene. So just pretend the alcohol wasn't there, right? Pent 3-ene using the new method. I'm not actually going to put that final E on there because I'm not done with the name. So I'm going to go back and get rid of that E. And then on the 2nd carbon, I have an all. I know it just sounds weird, pent 3-ene 2-all, but what it's saying is that I have 5 carbons. On the 3rd carbon, I have an alkene. On the 2nd carbon, I have an alcohol. Again, note, no final E. I just kind of think like that final E is the end of the word name, and since it's not the end, it doesn't go there. I know there's kind of a lot of weird rules. You need to do practice. There's practice problems in the book and extra practice problems. If I was to do it the other way, pent, the 3 is going to go in front, ene 2-all. That's the older way. So because the alcohol gets priority, right? My alcohol group up here gets priority. It gets the lowest number, but then it also gets the ending. Whichever method you do it in, because it's the highest priority group, it gets the final say. It's going to be the ending of the name. So if you're using this older method here, right, this older method, this 3 is going with the ene. And it's kind of weird, like why does one number go in front of the parent and then the other number goes at the end? That's kind of where the newer method fixes for it. So another example, let's do something that's cyclic. Let's not do that to you. I won't be that mean. Not yet anyway. Let's just stick a bromine on there. So numbering this one, again, my alcohol takes priority, so it gets the 1. And then the alkene is still going to have priority over a substituent. The bromine's just a substituent. The alkene is a functional group. I know alkylates are functional groups, but it's named as a substituent. So I am going to go counterclockwise. So on my 5th carbon, I have a bromo. That's an R. And then because it's cyclic and I only have 1 alcohol group, I don't have to put the 1 for the alcohol group. You can, it's not wrong, but you don't need it. So I have 5 bromo, and then I'm going to use the newer method. Cyclohex, and then 2 ene, and then all. Again, you're not putting that final E there because it's not the end, it's an enol. You could put 2 ene-1 all, but because it's cyclic again, and because I only have 1 hydroxyl group, you don't need to put it there. Using the older method, 5 bromo, 2 cyclohex, ene, all. Again, you can put the 1, if you do, it goes right here. You just don't need it. let's do, that's supposed to be a triple bond, and then let's put an alcohol here. So again, the parent on this one's going to be kind of weird. It's going to be this. It needs to contain all of my functional groups. So I need to have the carbon that has the hydroxyl group and that alkyne as part of it. The alcohol takes priority. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. I have a butyl group. Did I do this one up here wrong? I'm thinking of it. Sorry, guys. No, there's 5. 1, 2, 3, 4, 5. Okay, so I have a butyl group on carbon 3. I'm going to do the new method first. So I have 6 carbons. So hex. On the 5th carbon, I have an yne. I'm not done with it, so I'm not going to put the final ene on there, or the final E on there. And then on carbon 2, I have an all group. So 3 butyl, hex, 5 yne, 2 all. Other way, 3 butyl, 5 hex, yne, 2 all. And again, I'm slowly warming up to the newer method, but when you have more than one functional group, it just kind of makes sense to me. If you look at the second way I named it, the 5 goes before the parent, but then the 2 goes after the parent, and that can be hard to remember. Where if you just always do the parent first, like on the first way, then put the number right in front of, the ending. So 5 on carbon 5, there's an alkyne. Don't put the final E though, because there's another functional group on there. So then 2 all. Okay, so if we have both a double bond and a triple bond. So we're actually going to name them as ene-ynes, which so En and then ynes. You're probably going to have a number in between there saying where they are, but I'm writing it this way so when you put it together, you remember that the ene, right, the double bond, is going to come before the yne when you're listing the name. So it's not yne-enes, it's ene-ynes is how we're going to name it. And you're going to start numbering the parent closest to the first multiple bond. It doesn't matter if it's a triple bond or a double bond. You want to start numbering closest to the first multiple bond. If it is symmetrical, so a double bond on, let's say, carbon 1 from one end and the triple bond on carbon 1 from the other end, then my triple bond is going to take priority over the double bond. This. And then I have a double bond over there. This is a carbon-based group. And let's, put something fun on here. Sorry, that's a 6 carbon group. So my parent is going to be this. And then if I number it from the left, I have a multiple bond on carbon 1. If I number it from the other side, my multiple bond is on carbon 2. Because I want to start numbering closest to the first multiple bond, I'm going to go my original way. So 1, 2, 3, 4, 5, 6, 7 carbons. So on carbon 2, I have a cyclo, hex, and then there's an oxygen, so it's an ether, cyclo, hex, oxy group. And then I'm naming as ene-ynes. So let's do the new method first. My parent, hept, and then ene-ynes, the ene comes first. So on carbon 1, I have an ene. Don't put the final E on it because I'm not done. And then on carbon 5, there's an yne. So the ene comes before the yne. If you want to use the older method, 2 cyclo, hex, oxy, 1 heptene, still no final E on that, 5-ine. Either method works. I do think that once we start having alcohols and double bonds and triple bonds, the newer method I think is just easier. It sounds weirder in my book, but that's probably just because it's still new to me because I had only learned it the one way when I was in school. So let's do one more and then we'll talk about stereochemistry. Oh, we have some common, I just remember something else we want to talk about. Some common alkene groups. Kind of like we had like the isopropyl, we have a version for alkenes and things also. So what else can we put on here to make it fun? That's enough. So parent, and then I'm going to have to go up. And then this has an alcohol, an alkene, and an alkyne. And remember, the alcohol takes priority. So I'm going to start numbering closest to it. And then this one, I'm only going to name using the newer method. I would recommend just doing this using the newer method. On carbon 5, I have a methyl group. So that we got. And then I have 7 carbons, so hept. And then when you have an alkene and an alkyne, the ene's going to go first. So on carbon 3, I have an ene. On carbon 6, I have an ine. I'm not going to put the final E on any of those because I'm not done, because on carbon 2, I have an all. Because that alcohol group is the highest priority group, it goes at the very end. So 5-methyl hept, 3-ene, 6-ine, 2-all. Again, I think if you just do it this way, where you put the number right in front of the ending, right? So there's an alkene on carbon 3, so 3-ene. Just remember not to put the final E on those because it's not the end of my name. On carbon 6, I have an ine without the final E, and then 2-all. And then you just have to remember the order that they go in. Alcohols are always going to be last if you have an alcohol. In this in 235 and 236 it won't, but for us the alcohols will always be last. We're not going to have a higher priority group yet this semester. And then if you have an alkene and an alkyne, we're doing it in this order, the ene and then the ine. So stereochemistry, and this is for alkenes only, right? Because alkynes, if I look at alkynes, because they're sp hybridized, I can only ever have one other group attached to them. So I wouldn't have, are they on the same side or the opposite side, because they're linear, right? Everything's on the same plane. So there's no stereochemistry for these ones. I don't have to worry about cistrans. It's supposed to be an arrow and then the word no. Right? No stereochemistry. For alkenes, right? It's linear, sp hybridized. But for alkynes, I do have stereochemistry, and we've already talked about cistrans. So remember, cistrans are only if di-substituted. And not just any old di-substituted, each carbon in that double bond, right? Each carbon that has the empty, or the pi bond on it has to have a substituent. You can have di-substituted by having 2 carbon groups on the same carbon, but they have to be on opposite sides, right? And we talked about that also in the last chapter. If it's more than di-substituted or di-substituted, you can use this way for di also. So we're going to use what is called EZ nomenclature. So if, I don't know, we could say di, tri, or tetra substituted. And again, be careful, right? If I was to do this and then put 2 hydrogens and then 2 carbon groups, this is di-substituted, but cis-trans or EZ doesn't apply because both of these groups are on the same carbon, right? They have to be on opposite carbons because when we're doing this, we're looking to say, are they on the same side of the double bond or opposite sides of the double bond from each other? This doesn't work. So just be careful for these ones. I usually put something like that on a quiz and then you would like say neither, right? It doesn't work for those. So what we're doing with E and Z is we're actually going to assign priority to the groups, and it's the same priority rules that we use with R and S configuration. So assign priority. So to the groups bonded to the carbon-carbon double bond carbons. I know that sounds weird. When I do examples, hopefully it'll make more sense. And then once we do that, we're going to look to see if the highest priority group on each of those carbons are on the same side or if they're on opposite sides. If they're on the same side, it's going to be Z. If they're on opposite sides, it's going to be E. I just remember Z and then same side, so Z same side versus cis same side. You just make a Z sound instead to remember them. So Z same side. Let's just do an example because I really think this will make more sense once I do an actual example. And we'll draw one out using skeletal structures because sometimes that's a little bit harder. And it doesn't, like, this is disubstitute, it's a hydroxyl group, but it still counts, right? There's a substituent on that carbon. So if I look at the 2 carbons of my double bond, I have this carbon and this carbon, and there's 3 non-hydrogen things attached, right? I have a hydroxyl group, a methyl group on the one carbon, and then on the other carbon I have an ethyl group, and then there is a hydrogen here. So what we're going to do is we're going to divide this 2 ways. I'm going to first kind of look at it this way, and I'm going to look at the groups attached to each carbon. So attached to this first carbon, I have a hydroxyl group and I have a methyl group. Of those 2 groups, which one's higher in priority? Yeah, so hopefully you guys are thinking this group. So then I usually put an asterisk on the higher priority group is how I like to do it. You can circle it, you can just remember it, but I like to put an asterisk on it. So on that green dotted carbon, the highest priority group is the hydroxyl group. Remember, for priority, you'd look at the atomic number of the atom it's bonded directly to. So oxygen's higher than carbon, so the hydroxyl group is higher priority. If I then look at the pink carbon, right, this one here, it has 2 groups. It has a hydrogen and it has this ethyl group. So of those 2 groups, which one's the highest priority? Yeah, the ethyl group. So I'm just putting an asterisk up there again. So then what I'm going to do is I'm going to split my double bond just like we would if we were doing cis-trans. And then I say, okay, are my highest priority groups on the same side or are they on opposite sides? For this one, they're on the same side. So this is going to be Z. So my highest priority groups are on the same side of that pi bond, so Z, right? If opposite sides, and we'll do an example, it's going to be E. So Z, same side, E, opposite sides. So let's do a bromine this time. So again, I'm going to split it 2 ways. The first way, I'm going to look at just the carbons in the double bond. So I'm going to look at that carbon, the pink one I did. And what's higher attached to that, I have a bromine and a methyl group. Of those 2, which is higher in priority? So my bromine. And then I'm going to look at this other carbon, right? This carbon has an ethyl group. Oh, I did Z again. It has an ethyl group and a hydrogen of those two, which is higher in priority. That one. So then when I look down this double bond, right, those two higher priority groups are on the same side. So this one is also Z. Meant to do an E one for you. Sorry, I did a Z. Let's actually go back up and look at some of these ones we named, because we can do that for these too. So let's look at this one. I have this carbon, right? And that carbon has this group going down, and then it has a hydrogen. So this is going to be higher in priority going down. And then carbon 4, I have going up, and there's also a hydrogen on there. This group that's going up is the higher priority group, right? Hydrogen's never, just like when we were doing R and S, right? We're using the same rules. My hydrogen was always the lowest priority group, so that's never going to be my highest. And then when I split this right down my bond, that double bond, those two highest priority groups are opposite, so this one is E. And then that name, that would actually go right in front of it. If there was more than one double bond, you would then put 3 with it. Since there's only one double bond, I don't need to. Often it's in parentheses, just like the R and S. I usually don't make a big deal of the parentheses though. So that would go right in front of it. I don't do it with this, right? Alkynes don't have stereochemistry, it's linear, right? I can't look at the groups attached to it because there's only one group attached to it. So only with my double bonds. This one it wouldn't apply because I just have 2 hydrogens on this one, so no stereochemistry. That's just an alkyne. This one, you could just use cis if you wanted. This one, you could use trans if you wanted, or you could do, put trans in front of it, or if I wanted, I could use E. Either one works. If it's cis or trans, you can use Z or E always. You just can't always use cis and trans when it's Z and E. Right? Cis and trans, if I go back down, it's a ways down now. Right? Only. So let's do another one. We'll actually name this one. Okay. So my parent is going to contain all of those double bond groups, right? It needs to contain both my alkenes. I want to number it so I get the lowest number for my alkene, so I'm going to start from this direction. I usually name it and then I go back and do the stereochemistry after, so I'm just going to name this. On carbon 5, I actually have a carbon 3. I just want to move it over so I have room for stereochemistry. I have a sec but not oxy. So sec butoxy. On carbon 4, I have a bromo, and I alphabetized those wrong. Sorry guys. You do alphabetize the sec butoxy based on B, and the bromo is also on B, but it's BR versus BU. I just had the B for butoxy in my head and just put that one first. So anyway, substituents always are alphabetized. So on the 4th carbon, I have bromo. Bromo comes before my sec butoxy group. Sorry, I alphabetized those wrong. So BR comes before BU. And then I do have 2 double bonds, so we're going to use the Diene. I'm going to use the newer method, so hepta, that A goes in there if you have more than one, and then 2, 4 Diene. If you wanted to use the older method, 4 bromo, 3 sec butoxy, 2, 4 heptadiene, you just move that 2 and the 4. I do have the 2 double bonds, so I do want to include stereochemistry. So I'm going to look at the first one, so the one that starts on carbon 2. I'm going to look at the 2 groups attached to carbon 2. That's a hydrogen. And the methyl group has priority over that hydrogen. I'm just going to get the hydrogen back out of the way. I'm going to then look at this carbon and then which of those has highest priority. If I go up to carbon 4, it's a carbon. If I go down, it's an oxygen. So that has priority. So then when I look down that double bond, those two highest priority groups are on the same side. So on carbon 2, it's going to be Z, so 2Z. I'll go back and put this in front in a minute. On carbon 4, I also have to look at the stereochemistry. So on this carbon, let's use a different color. On this carbon, I have a bromine. If I go up, and then it goes down to a carbon, so the bromine is higher in priority. On carbon 5, I have an ethyl group. If I go down, I have a hydrogen. That ethyl group is higher in priority. So as I look down that double bond, that one's also Z, so 4Z. So in front, I would have 2Z, comma, 4Z, and then that would go in parentheses. So whenever you have a double bond or, just a double bond, as long as it has stereochemistry, or it had one up here that didn't somewhere, wherever it went, I guess I've lost it. Somewhere, this one, right? Because I have both hydrogens, I can't pick priority over those are the same, I don't have it. So unless you have some instance where the two groups on one of the carbons is the same, you're going to have stereochemistry with alkenes. Alkynes, no, right, because they're linear. So the last little bit that I want to talk about are those special functional groups, and then we'll be done with nomenclature. So common substituent names. So this is if we have a double bond that needs to be a substituent, and I'm only going to do it with double bonds. So for alkenes. And we're only going to use this if we have to. And usually it's pretty obvious if you have to. I'll do a couple examples so you can see. But if I have the double bond actually attached right to my group, so that little squiggly line is where it's attached to the parent. And when we do one, hopefully it'll be easier to see. This is called a methylene group. If I have, and we know this when we're talking about vinyl halogens, right? Vinyl halides, if I was to put a halogen there, it would be a vinyl group. So that's the name of this one. If it's attached to another carbon there, it's a vinyl group. And then allelic, that's our other one, so allele. So one away from where it's attached, this would be an allele group. So sometimes these are easier to see if I put them on a ring. So if I do this, and then let's put an alcohol on it. So if I was to name this, this is going to be carbon 1 because it's an alcohol, right? That's always going to be my highest priority group. And whether I go clockwise or counterclockwise, that methylene group, it's going to be on the same carbon. Right? If you have a ring and the ring is your parent, then it's the whole ring. I can't do this. Like this isn't something you can do, right? Because then how do you name 5 and 6? So if you have a ring and the ring is your parent, the ring's not always your parent, but if the ring is your parent, then the ring is your parent. Don't go out to that other group. So then the problem is I have this double bond that isn't part of my parent. So I don't name it as part of my parent. I actually name it as a substituent. So this one, when I name it, I have cyclo and then hexanol, right? I don't have to put the 1 there. But then on carbon 4, I guess I didn't leave enough room here, so let's move it all over. I don't really like the green either. On carbon 4, I have that methylene group. So 4-methylene, and then cyclohex and all. So basically that double bond, that alkene group, just becomes a substituent. Another example, I could do this. Oops. I'm going to put an alcohol group here. I'm going to put an alcohol group here. And then I'm going to put a double bond here. So now my parent needs to contain both of those, which means that double bond again now is not part of my parent. So because it's not part of my parent, I'm going to name it as a substituent. In this case, it happens to be a vinyl group, right? Where it's attached. If you look at this, that's what this guy is. As far as numbering it, it's symmetrical. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So either way, it's symmetrical. So on carbon 3, I have a vinyl group. And then I have 2 alcohol groups, so 2, 4, I'm using the older method here. And then I have pent. And then remember, if you have 2 carbons, you do the whole ending and then diol. 3 vinyl, pentane, 2, 4, diol using the newer method. So again, it's generally pretty obvious when you have to use them. Basically, there's no way to do this last one we did where I can get all the things that need to be in the parent. So the double bond isn't then. The alcohols have priorities, so they get to be part of the parent.